value of sparsest cut, STP, is order of alpha of g n over log n. And the integrality gap is just order of square root of log n. If V1 is a definition, if V1 Vn is in Rd and delta is greater than 0, then they are delta separated. We say they are delta separated if they are really delta separated. So it's obvious. And we use theorem 1. For any C, there exists C prime such that any C spread unit L2 representation contains delta separated subsets S and T, where delta is B over square root of log n. And there is a randomized polynomial time for finding these subsets S and T. The corollary to the theorem is that W is the optimum value of STP. So if you solve that and then you replace it, you substitute it in this measure, Vi minus Vj squared. Since the condition is satisfied because you solved STP, so you have already satisfied these conditions. 4C minus C and 2. And then we can show that how to produce C prime balanced cut using corollary 2. So there exists a randomized poly algorithm that finds with high probability a cut that is C prime balanced. And we use theorem 1 first because we want to produce delta separated sets. If we create some delta separated cuts S and T, so they are separated. I mean, this is the distance is delta, and let's call the edges going from this way to the other one to be ER, and then this area is VR, and let's say we have some VJ here, some VI here. This area, let's call it V0. I mean this area. All of them is V0. Then an interesting thing is that after we created these subsets, it's an algorithm for that. I will explain it, but assume that we have created such a delta separated sets. Okay, then we produce the cut. I mean, we pick a random number R. It's like it is inspired by the max cut problem. It's like this. Again, we have a random number, and in that article that I explained, it was a random hyperplane. Here we have a random number R, and then we output the cut simply by say, okay, cut is VR minus, this is our cut. And by definition, for example, something VS is all VIs that VI minus a set is less than S. So to bound the size of the cut, which is ER, where each edge only contributes to ER for R in this interval. So assume, so let me give you another page. So this is what I said, and there is a margin here. So some of the edges are like this. Some of the edges are like this, like this. So what I want to say is that the triangular inequality, of course the distance between them is delta, and this is t, and this is s is v0, and r is here, this is r1 for example is here, r2, this is r2, and so W is the measure that you want to minimize, Vi minus Vj squared, is We. This is by definition, and this is greater than the expected value of. The expected value is integral, is just an expectation. So it's smoothed very sharp things. So the expected value of ER over the interval is at most W over delta, and the algorithm produces a cut of at most 2W over delta, which is order of W log n, with probability at least half. So let's go and see what algorithm did I promise you that can create delta separated sets. So the algorithm is very easy. You input a C-spread unit L2 representation, V1, Vn in Rd, by solving that semi-definite programming. So now you have this input. And you want to round it to say which one belongs to which cut, which S or S bar. And the parameters, the desired separation delta between S and T. Delta is S and S bar. Delta is a parameter. The projection gap is a you will see what is that. And we compute the largest. And in step 1, you project the point, your vector, these are your vectors. This is a vector, just with the same analogy and inspiration from that Max Scott algorithm that use a random hyperplane. Here again, we are using randomness, but here we project it into U. For example, here is your hyperplane. And you have another hyperplane here. So this is the margin. So this is the gap. We don't want any. We try. We cannot find it. We try not to have any points here. But so any points here, we project it into this. Line. So any point here, we project it into this line. And this line has a value on each. It's a 1D line, so the inner product of any two vector, V and U, is, but U is random. So U is a random, that random element that I showed you. So by projecting all of your vectors into this line, we have the one-dimensional, a scalar, you get a scalar, and then we can say that we compute the largest value m, that half of the points have v and u greater than m. So half of the points are here, half of the points are here, and here is a gap. So S of u is the number of vertices that vi and u is greater than m plus sigma over square root of d. And tu is all of the vertices that are on the other side of hyperplane 1. So we have just one hyperplane, but I have sketched hyperplane, two other hyperplane, just to say that there is a gap within them. There is a gap so that you can rarely find such vertices like this and this. And the algorithm is that if you find such vertices, you just delete them. You pick and you repeat this until that all of the vertices have some destiny. So Ti is the inner product of Vi and U is less than M if S of U is less than 2C prime N. If this happens, halt. And we can prove the probability of halt is small, and that's why. So you see, the idea is very, very similar to the idea of Goemans Williamson in 1995 that I explained for the max cut problem. And in there, but now here we have like this. These are two other, the projection of them, and this is your U, and here is S of U and T of U, and this is the gap that I showed you. So all of them this is just 2D of the previous slide that I showed you. So we are lucky. We are lucky because the probability, we are lucky because the likelihood of halting is very small. And the challenge is to show that delta separated sets are large. I mean, it means that no more than C prime n pairs are deleted from SU and TU. And so here is another picture for you, U, V, and projected, which is U and V, the projection. And you see it has so the nice properties of Gaussian distributions, e to the minus t2 over 2. If you plot it over all of the vertices, U and V, but one of them is random, So we apply all of the vertices here to see if we can find a concentration measure or not. And the probability that Vi, Vj get stretched, and what I mean by stretched, it means that Vi, Vj, there exists such that their difference is less than delta, but Vi minus Vj and U is greater than this. So here it happens very rarely. And so if you calculate the expected number of stretch pairs, order of n2 xp minus log n, so you got the idea. I don't want to bother you more. I want to talk about expander flows, which is the last part of this lecture, expander flows. So the value of SDP for sparse cut SDP for sparsest cut. So this one approximates or certificate for expansion. Expansion at least order of alpha over log n. So what I mean by that, I mean alpha star expansion, I mean the optimal expansion. First of all, I should say that f of x, for example, this could be your SDP optimal point, but not the optimal, just SDP opt. It is less than rho optimal if you have a rho approximation. It is sandwiched between this. So for minimization, use this. And you should know that rho is greater than 1. For example, here our approximation, you see log here, so that means that square root of log n, and you know this is greater than 1. So this is for minimization. But if you have a maximization problem, in maximization, rho is less than 1. So for example, in max cut, if you remember, we got 8785, I guess. It was less than 1. And f of x in any maximization problem, it is sandwiched between opt and rho opt. So for example, here, if you just apply it here, we can say that SDP opt is sandwiched between alpha star, which is the real optimal points, optimal value, and log n approximation, alpha star. So this is the optimal, and SDP opt is, and this is the factor which is rho. So I reviewed some computer science, and now your graph, G, we have V and E, you have expander, you have a weighted expander, each edge has a weighted expander. So the same vertices, you see, but the edges are different. Also, you have some weights. Here you don't have any weight. In G, you don't have any weight. And Aurora has an Kale. In 2004, they showed that order of log n approximation to sparsest cut you can find in O tilde in 2 time. And for that, you need some definition. For example, sparsest cut is phi of W is minimum of demands from going from source I to source J, cardinality of SS bar. And similar for alpha of W, you can define that. And then you need to know what is DI, so the sum of all. So degree of node I is sum of Dij over J. And weighted graph is deregular, if and if all degrees are D. And now I can show you multi-commodity flows. Multi-commodity flows as graph embedding. So it's a generalization of single commodity, multi-commodity flows. We can do it with multi-commodity as well. So in multi-commodity flow, we assigned assignment of demands, Dij, to each node. For example,